So let's see, this afternoon I would like to talk about a recipe, not for food, but for HPC software and application at Exascale. I'm part of this KAUST supercomputing laboratory. KAUST is a freshly new university, has been created 3 years ago, close to Jeddah in Saudi Arabia. But before that, I would like to give some credit to the HPC Council, Advisory Council, for giving me the opportunity to give this talk today. As well as some collaborators here, my former employee, ICL, at the University of Tennessee, folks at INRIA Bordeaux, and people as well at the University of Colorado, Denver, Colorado. So here's my outline. I'll start with some motivation, explaining or showing some background for some dense linear algebra libraries, high-performance libraries. I move on with this new project that we started a couple months ago. This is called Morse project, Matrices over runtime systems at Exascale. And then I have three toys, or three benchmark, or three code to emphasize on the ideas that I think are necessary to reach Exascale in terms, at least on the software side. So there are two dense applications, the Cholesky-based matrix inversion and the generalized symmetric eigenvalue problem. Those two algorithms have really some simulation or application behind it. I moved then with this n-body simulation, which is kind of dense as well. And I'll show how we could use those runtime, those dynamic runtime to be applied outside of usual linear algebra libraries. And I finished with this seismic application. This is still an ongoing work, so not that much result over there, but mostly ideas. All right. So the K computer, I think it's difficult to give a HPC talk without mentioning the first fastest machine in the top 500 list. So this is made by Fujitsu. The K computer is right now, I think, in Riken, in Kobe, in Japan. So it has a striking number of core right there, 640,000 core. It reached up to 10 petaflop with this LAPACK benchmark. And when you look at it, when you look at this international Exascale roadmap software, they have this barrier of 20 megawatt. I think many people before me talked about it. And when you look at this number here right now, they reach, I think it's not mentioned actually in the slide, but the power rate for that machine is 10 megawatt. So you're talking, so 10 megawatt, 10 petaflop, right? So you're talking about achieving 2 orders of magnitude in terms of performance to reach Exascale by only doubling twice the power consumption. So it's pretty striking there. Along with the fact that you have 640,000 core, so you have a huge level of parallelism there, and you need some sort of tool or libraries which could really handle those core appropriately. So actually there were, maybe I need to mention this funny story, because you guys seems to be kind of sleepy the whole during those 3 days, no question, nothing happening here. So there is this funny story. Last year, when the K computer was revealed to be the fastest computer in the world, so there were some journalists asking questions to the two people leading this project of the K computer, and the question was the following: what is the MTBF for that for that machine? Great, it runs for it ran actually for more than 30 hours to get this number, this LAPACK number, and the question was, what is the MTBF? Okay, what is the mean time between failure? So the two Japanese guys, look at each other, talk each other, and then come back and said, well, it failed once, and we're still waiting for the second time. All right. Okay, so this is my HPC recipe for Exascale computing. There are a lot of keywords there that I'll be mentioning during my talk. Power efficiency, big deal. Fine-grained parallelism, you're going to have a lot of cores to be able to exploit efficiently. Auto-tuning, of course, you don't want to redevelop, re-implement the design of your core kernel of your application, because now you have a new hardware coming up to play. Data motion reducing, synchronization reducing, and of course here I put it on the top, some kind of dynamic runtime system which will help you in a productive manner to exploit the underlying hardware architecture. And we heard many times this hardware and software co-design. So this is, of course, very crucial because software guys by themselves, they won't be able to achieve this exascale by 2018 if they don't work together with hardware guys. And I guess you get this 10 to 18 over there. At least in the software side, we've seen this kind of collaboration between hardware, in software dense linear algebra. We've seen this kind of collaboration going on between hardware people and software guys. So if you look at the 70s, we had this LAPACK library based on vector operation. And it used mainly level 1 BLAS operation to suit this vector machine at that time. We moved then in the 80s with LAPACK, which used block algorithm. And if you look at the history, it was by the time where the Beowulf cluster, not the Beowulf cluster, the cache memory cache hierarchy architecture was born. And those rely on level 3 BLAS operation, which are more compute intensive. You have more data reuse there. And in the 90s, we moved with ScalaPack, which is a distributed version of LAPACK, targeting Beowulf cluster at that time. And they relies on PBLAS message passing to communicate between the different nodes. In the last decades, we've been working with my other colleague into developing new new linear algebra algorithm to tackle the multi-core architecture as well as the GPU hardware accelerator. Mainly Plasma and MAGMA project. And I'm going to talk about those two guys in the next few slides. So if you look at LAPACK algorithm, so this is, they are really characterized by block algorithm, meaning that you have this panel and update sequence. Okay, this is the main component of the algorithm. You do some operation, blast 2 operation within the panel. Those transformations, again, are memory bound because they are level 2 BLAS operation. You don't have that much reuse there. So then once you're done doing your operation on the panel, what you need to do, you accumulate those operations and you apply them in one shot to the trailing submatrix using BLAS 3 operation. Okay, so think of GEM, for example. The problem with those algorithms, those block algorithms, meaning LAPACK mainly, is that the parallelism is really hidden inside the BLAS. So to be able to extract the parallelism from your architecture, you rely on a highly optimized vendor BLAS. Okay, so this is the way you would run faster with LAPACK. And by doing this, you have this fork join model. So you call a gem, let's say, you fork, you have threads working on your gem, crunching some numbers, and then you join, and then you do some other calculation, and then you call another gem. So again, you fork and join, and this is really a bottleneck, at least on multi-core architecture, and. So this is here a cartoon showing some of the ideas that I mentioned in the slide before. So this is my matrix here, square matrices, and let's say I'm doing this LU factorization. The gray part is the matrix which is already factorized. This is my final result. And I'm working on this panel here, doing some BLAS 2 operation, which are memory bound. Once I've done with those operations here, I try to accumulate them such that I can apply them in one shot to the trailing submatrix here, or the remaining matrix which has not yet been factorized. And for that, I use BLAS 3 operation, which are really compute intensive. So the problem is that you have this panel update sequence, and the way it is implemented in LAPACK, you don't do any overlapping. So you do panel, once this is done, you do update, when this is done, you move to the next panel, and so on until your whole matrix is factorized. So this is the state-of-the-art package LAPACK. This is the way it's implemented there. It's another cartoon just showing this fork join principle or paradigm. Okay, so you would fork and join at each step here, but you would never have, you would never fork your threads in the beginning of your application and working all in parallel until the end of your computation. But you would really fork and join, fork and join, fork and join. Okay, so Plasma. So this is. It is a new library. Well, it's been there I think for maybe 4 or 5 years. It's intended to eventually supersede LAPACK. So we had to really redesign all the algorithm within LAPACK. Okay, so mainly, so we try to take the parallelism which resides originally within LAPACK inside the BLAS. We try to bring it to the fore, and this may require the redesign of linear algebra algorithms, and by by bringing to the fore the parallelism, we were able to remove a necessary synchronization point that we've seen in LAPACK between the spanner and update. And what you can then look at the new algorithm as a DAG, basically a directed acyclic graph, where the node represent tasks and edges define dependencies between them. So we use a dynamic runtime system here called QUARK, which is shipped within Plasma. This runtime basically look at the different tasks being queued and just schedule them on the available computational resources. And for that, we had to go for a tile data layout translation. So if you look at the way LAPACK stores the element of the matrices in memory, this is the column major format from LAPACK. And you can see they are all contiguous in memory column-wise. And the Plasma came up with this new tile format, okay? Not really new, I mean, it has been actually discussed by previous people, but we were able to reuse it to our benefit. And the idea is that you split now your matrix into some blocks or tiles, where now each element are contiguous in memory within each tile, okay? So this brings a lot of improvement in terms of, trying to reduce the number of cache misses and TLB misses. And the idea is to try to tune actually that block size to fit the L2 cache of your multi-core architecture. All right, so another library, which is MAGMA. So MAGMA, the idea behind MAGMA is the following, is that I take the LAPACK algorithm, and the most compute-intensive kernel that are called within LAPACK, I just offload them to the GPU. So just by doing this, we were able to accelerate LAPACK considerably, but still we wanted to do more on top of this. So we tried to learn from the other project, Plasma, meaning we went ahead and actually split the original matrix into tiles and tried to have now a runtime which could run the different tasks there on the GPU as well as on the CPU together. We use the StarPU runtime system from INRIA Bordeaux because as of today, QUARK does not handle really the GPU, the coprocessor of the GPU as a resources, meaning Plasma is really focused on x86 only. So with MAGMA, we had to collaborate and with some of our colleagues at INRIA Bordeaux. So and we use their StarPU runtime system for that. So, and the nice thing about StarPU is that I'm going to say a few words about those runtime in the next slides, but the nice thing about the StarPU runtime system is that you can really run your application using both CPUs or CPUs and GPUs, which is not really straightforward because I think most of people when they focus on GPU, well, they just run on the GPU. Or if people don't want to look at GPU, they just run on the CPU. But you can actually run really both together as long as you provide the appropriate kernel. Meaning a kernel which could run on the CPU and a kernel which could run on the GPU. All right, dynamic runtime system. This is a slide, the general slide, saying that we're trying to have a runtime, a dynamic runtime, which run this DAG dynamically. So you may have an out-of-order execution flow of fine-grained tasks. So the idea is that as soon as the data dependencies of a particular task are satisfied, I just get scheduled. So think of it as a producer-consumer. I think one or two people in the workshop mentioned this concept before. So when you look at it, really, try to sit down and look at it. I mean, it's a DataFlow programming model we're talking about here, right? So it's a 5-decade-old concept. It's not something new. We're not reinventing the wheel. It just, it's there for a long time and looks like old concept, can actually participate into trying to make our life easier on the new architectures. So it's a programming paradigm that models a program as a directed graph of the data flowing between operations. You should think of it as how things connect, really, rather than how things happen. It's like an assembly line, right? So the project is here, I just do something about it, and I move on. I pass it on to somebody else, and so on, okay? So it has very nice features. It's inherently parallel, okay? And we could really exploit it by having an efficient runtime system. All right, so that was my motivations. I'm going to spend a few minutes here about this new project called Matrices over Runtime System at Exascale. So the three institutions that I mentioned in the beginning are working on this project. We're all working on it together. So the mission statement is the following, is to try to design dense and sparse linear algebra methods that achieve the fastest possible time to an accurate solution on large-scale hybrid system. So there are mainly two things that we want to focus here in this project. The first thing is to have efficient runtime, okay, to be able to handle the complexity, the ever-growing complexity of the new architecture coming in, and at the level as well as the algorithmic, the algorithmic design. And we need to come up with new algorithms so that we can exploit the hardware capabilities at most. So I'm going to discuss here a couple runtimes more into detail that are part of this project, okay? Because there is one component about, again, there is one component in this project MOS, there is one runtime component and there is one algorithmic component. So this is, I'm going to discuss here the runtime component. So there is this QUARK, which is developed by the University of Tennessee. It's shipped within Plasma. It's actually a project by itself now. You can just go ahead and download it from the web without, without the need of downloading Plasma with it. So the whole idea of those runtime system, and in particular QUARK, is it looks at your sequential nested loop code, and it takes it, look at it, try to define, try to look at the different dependencies that exist between those tasks, and then run it in parallel. Okay, so it's a task-based parallelism. This runtime has so many options, and I'll be mentioning some of them, which are the most relevant, I would say. One of them being this, being able to give us different size to define windows, the window of tasks here. So such that if you have a small window of tasks, well, you won't be able to do any look ahead. Okay, you won't be able to overlap your different tasks. But if you have a large enough task size, you can really try to do things ahead of time, as long as the dependencies are satisfied. There is this data locality and cache reuse flag. It's a flag that you would decorate one of those tasks and say to the runtime that this guy, you better make sure that the thread who just ran that task, the next task should be run by the same thread. Okay. So it has a high user productivity, as you could imagine, because the starting point is really your sequential code. Okay. All right. So this is one slide about the internal of QUARK. So this is the user code. It can be in C or in Fortran, which is composed of those insert tasks. Let's say in that case you have 8 different tasks, and you need to call this API called insert task, which define the function. Tell to the runtime QUARK what are the different parameters of that function, whether they are input, output, whether they are in-out, whether there are no dependencies. And then the runtime will look at those different data direction, and we'll do something smart about it and hopefully do the right scheduling. So the way it works is that you have a master thread which will unroll your sequential code and queuing the different tasks, and then at the same time the worker thread will start picking up those tasks as they come in and just execute them in parallel. So this is a story about QUARK. This is the way it looks like for a kernel called DPOTRF, which is one of the main kernels for the Cholesky factorization. So there is this API QUARK insert task, and you specify what is the name of the task in part here, and the different parameter and the different direction here. Again, whether it's in-out, whether it's output, and some flag here that you could mention as a hint for the scheduler. And here, this is the definition of the task itself. Okay, StarPU. So as I mentioned before, QUARK just focus on x86. StarPU will focus on x86 plus GPU altogether. So it has to provide memory management, right? Because all of a sudden you're dealing with different memory those on the GPU, those on the CPU. Although with this new UVA, I think those guys did some pretty good job by handling it appropriately now. Okay, so I think their model for this memory management has become less difficult by this introduction of NVIDIA, this UVA. So it supports SMP. x86, NVIDIA GPUs right now, OpenCL devices, cell processors, and the whole stack, software stack, or the whole, not software stack, but the whole stack looks like this. You have your application here, parallel compiler, or parallel libraries that you can rely on, and you can now depict your sequential code into a DAG, and then the runtime will jump in and take this DAG and schedule it, whether it could be on the CPU or on the GPU. And this is the way the API looks like. As you can see, it's very similar to what QUARK is doing. Okay, it's very similar to what QUARK is doing, except that StarPU again will run the different kernel on the GPU or on the CPU. And this is again it can be let up to the user to decide which kernel needs to be run on the CPU and which one needs to run on the GPU. SMPSs, this is the last one of the, I think this is the last runtime system. This is developed by some of the guy in Barcelona Supercomputing Center in Spain. It's a compiler technology. It's really different from the two other runtime that I mentioned. So in the sense that they have pragmas now in your sequential code. So again, you need, as a user, to define the different directionality of your task parameters. And then there are some internal, as you can imagine, since it's a compiler technology, it translates your C code with your pragmas annotation to some C99 code. And there are some features as well as for data locality, data renaming as well, to enhance further the code. Okay, so this is the way it looks like simple Cholesky sequential code. You have your 4 nested loop here, or 3 nested loop here, and you have this pragma, you say start, pragma finish, and here in the middle you have your different tasks that you have defined, and each of those tasks there, in their prototype, you mentioned the pragma, you mentioned in the pragma the different parameters name and what are the direction, okay? Of course, standardization, right? So I mentioned 3 runtime systems which are really having the same concept, even though the SMPSs is a compiler technology. But the API is very similar. Well, why not trying to put some effort there and define a common API standard for this runtime system? It's a difficult task. It's a very difficult task because you want to make sure everybody is happy with whatever standardization you end up with. But it's still work in progress. Here, I just have 2 slides here about this new framework that implemented by the University of Tennessee people. It's called DAG. So this is an engine. This is really a DAG engine. So it's a compiler technology, and this DAG really focuses on distributed memory system. Okay, because what I mentioned, QUARK, SMPSs, and StarPU right now, they only focus on shared memory. Okay, so the DAG framework gonna tackle the hard system, distributed system, and but again, the way they approach it, they look at the sequential code again. Okay, so their starting point is the sequential code. So what they do basically is that if you look at the stack here, so the starting point again is this input serial code. They have some compiler technology here using this Omega test. I'm not too familiar with this tool, but basically try to understand or try to determine what are the different search space of each variable in your code and try to find the dependency automatically here. All right. So you end up having a file called job data flow, GDF. It's a GDF file, we call it. And the user at this point can come in and try to do some change, or actually even try to check whether the compiler job, or whether the compiler has done a good job or not. And if not, he can, go back to his input serial code and do maybe some change to help the compiler understand what's going on. Once the GDF is obtained there is a translator which now defines the different task and the parallel task. This is added with this Runtime library, okay? And this is fed into the system compiler and executed using MPI and thread. So it's a new project. I think it's been there for a year, about a year, maybe a year and a half. And this project is eventually, again, supposed to supersede LAPACK. All right. Okay, so more fun stuff, hopefully, here. So I'm going to start with these three test cases. The first one are really dense algorithm, the Cholesky-based matrix inversion, and this generalized symmetric eigenvalue problem. Okay, so yes, so people are actually building A-1. Okay, so yes, seriously, they really want this inverse, the matrix inverse of the symmetric matrix inverse. They really need it. Where in the field of statistics, to understand the critical component, it's a critical component of the covariance matrix. So to get this to get the inverse of the matrix, there are three steps. You compute the Cholesky factorization of the current matrix. You invert the Cholesky factor, and you do some product of this inverted Cholesky factor to get the final inverse of the matrix. Okay. So there are three steps. Okay. They are all really compute intensive. Okay, and we use TARPU, the runtime system here, to do the experiment. I just want to throw in this slide before I show some result. This is the hybrid architecture targeted. You have your GPU sitting here as a coprocessor. You have your x86 here with some host memory, and you have this thin, really thin pipe, this PCI interconnect between the host and the device. And when you look at some numbers, performance number, these pipes give you 64 gigabit per second. And when you look at those horses, how much they can achieve, it's 515 gigaflops. So you have kind of an order of 10 there, right there. And what this tells you is that the idea is that you need to make sure you leave the data as much as possible in the device memory. Once it's there, make sure it stays there as much as possible. Do all the operation that you need to do on this data prior to put it back to the host. Okay? Sure. So auto-tuning, right? But not this type of auto-tuning. We need to choose the right NB or the right tile size. And this is really critical when it comes to running on the GPU as well as on the CPU. So this slide, I'm sure now all of you guys know it by heart. But there is a thing, some stuff that we've done back at ICL. When we had this Tesla and then we got the Fermi, we really went and redesigned those kernels that we had because there were really a major change going from Tesla to Fermi. Okay, we paid the price. It took some time, but at the end we had nice stories to tell. But it was really, time consuming. We don't want to do this anymore, really. So especially because, we hope that there won't be, dramatical change in the hardware architecture going from Fermi to Kepler and to Maxwell, although it's not given. So we need some sort of really automatic auto-tuning, okay, which could determine what is the right kernel, the right parameters of the kernel that we have sitting there, to be able to run on Fermi or Kepler or Maxwell. So this is still a work in progress, although right now we just use the standard prune search, okay? So we know more or less what are the search space of some of the variables that we are looking at, and so we try to reduce it as much as possible. So far so good, but we are thinking of more an automatic manner, an automatic procedure to get those right parameters. Okay, so those are the preliminary results that we had published at HIPS last December. So this is, the standard performance graph, matrix size in the x-axis. In the y-axis, we have the performance in gigaflops. So I'm showing 4 curves there. The blue one is when you run LAPACK on the current architecture, which is an 8-core Xeon-based with 2 Fermi 2070 attached to that host. So 8 core and 2 Fermi. So when you run LAPACK, you get around something around 50 gigaflops. When you run LAPACK Plasma, okay, which run only on the x86, you do definitely better than what LAPACK is doing. When you run MAGMA with one GPU only, okay, so you use one core dedicated to that GPU, and most of the computation happen on the GPU, you get kind of a boost, but you're very close to what Plasma is doing on 8 CPU. So one GPU gives you kind of the performance of 8 CPU, okay? And then when you do this hybrid computation, you use 8 CPU as well as the two GPU, the two Fermi available there on your board. You get really a huge jump in terms of performance there. And so, and if you look at the curve of MAGMA, you see that, because you're using only one GPU, you're limited in terms of memory. You cannot exceed, certain size of your matrix. While when you use this hybrid computation type of scheme, you use all the memory available on your system, whether, your hybrid system. Any question? All right. Okay, the next problem, the next problem is this generalized symmetric eigenvalue problem. So this is the equation we want to try to solve. So A is symmetric, this is the property of A. B is symmetric positive definite, and we want to find the eigenvalues as well as the corresponding eigenvector X. This equation, solving this equation, is really used to obtain energy eigenstate in chemical cluster theory, electronic structure of semiconductors, ab initio. So it's not just a toy. There are really applications behind it. And if you look at this equation, the way to solve it, there are 4 steps basically to solve it. Again, you do a Cholesky factorization on your matrix B. You apply those triangular factors that you just computed to the left-hand side of your equation A. When you get this A, modified A now, you reduce it to tridiagonal form, okay? And once you have this tridiagonal form T, you apply this QR iteration from LAPACK. You just call LAPACK here, and to get the eigenvalue, the corresponding eigenvalues. And so this is the first, step number 4 is really, it's n square, okay? It's basically n square compared to the other 3 first step here, which is n cubed. You have really, it's really compute intensive. So the last step, we just offload it into LAPACK. We just call LAPACK sequential, as this is not the main part that we want to really optimize. So the part that we really want to optimize is 1, 2, and 3. Okay, so this is 3 DAGs I'm showing here. This is stage 1, 2, and 3. Again, the 4th stage we don't look at it. 4th stage we don't look at it because it's not that relevant. It's really n square. So those three stages. So this is 4th stage, first stage, 2nd stage, and 3rd stage. And you can see that this is a small matrix size or a small tile size. I think it's maybe a 5 by 5 tile matrices. But I'm not sure. I think 5 or 6. And what's happening there is if you apply those tile algorithm IDs on the first stage, while you end up having a DAG that way, and then this is your first stage. If you apply again those same IDs in the 2nd stage, you get a DAG that way. And same for the 3rd stage, all right? But if you want to combine all stages together, and this is the idea behind using this dynamic runtime system where the task gets scheduled as soon as the data dependencies are satisfied, you end up having such a DAG where you can see you start working on the 3rd stage while you start working on the 3rd stage while you're still working on the 1st stage, okay? So this is pretty, I think, nice to have such a possibility. All right, this is another way to look at it, okay? So I'm trying to find the eigenvalue of a certain matrices. And, this is the way to look at it. If you were to plot your matrix at some point within your computation, you can see that you would have reached already the eigenvalue there, okay? While you're still working on the other stages, different stages on the other part of the matrix. So here are the graph in terms of performance. We have the matrix size here in the x-axis, time in second, elapsed time in second in the y-axis. So the lower the better. Okay, the lower the better. So we're doing 10 times faster than LAPACK. And this is on, I forgot to mention, this is on a Magny Cours system, 48 core. So no GPU there, no GPU, just x86. And I think we are 3 times faster also than the optimized Intel MKL library. Okay, some plots about power, right? So one of the ingredients I mentioned before was, those power efficiency. So we try to look at the energy footprint of this algorithm that I just mentioned previously. And the way we do it, we had access to a Virginia Tech system which used this PowerPack software tool. So the idea is that, this is my cluster, and I look at a single node, because, I'm running Plasma. Plasma is just a single node. So we just actually use the single node of that cluster, and there are many small hardwares or power meter, which allow you to collect the actual power consumption or power rate on a component basis of your system. Okay, so maybe if I show the slide, it will be better. So I'm looking at this power rate of LAPACK, right? This is LAPACK tridiagonal reduction. So we have 5 curves here. So in the x-axis, we have the time in second, and the y-axis, we have this power rate, okay? We have 5 curves. So the red is the system one. Think of it as the overall system power consumption or power rate. The green one is only the CPU. The blue one is only the memory, and the 2 over here, which are not really relevant, but I put them there for fun. This is the motherboard and fan, so they don't really interact, they don't really produce any relevant information, but I just put them there for fun. So when you look at those peaks here, okay, so if you look at the system here, the red curve, when you look at those peaks, right? So this actually happened when this is an update. So this is LAPACK, right? LAPACK has this panel update sequences. Panel is memory bound. Update is compute intensive. So those peaks happen when I'm actually doing an update. Okay, and then when I have a dip, this is when I'm doing a panel. And this matches perfectly between the CPU, when you look at the CPU and the memory, right? So a lot of issues happening, a lot of contention happening in the memory, because when you do the panel, it's blast 2 operation, you're putting a lot of stress and contention on your bus to get the data into your cache. And this engenders a lot of contention there in the memory. So this is the story for LAPACK. This is the energy footprint of LAPACK. We're gonna do the same experiment, but with Plasma now, okay? So with Plasma, by chopping your matrix in 2D into tile, okay, you basically reduce, dramatically the number of cache misses, okay? And you can see that those curves are more smooth now. You don't have any more the high peaks there. And the other thing that was actually very nice, is that you can see clearly there is something else going on in your algorithm, right? So I think the first time when I've seen this curve, I was really, excited to see that. So we are doing in this 3rd stage of this tridiagonal reduction, we are doing actually, we're reducing that matrix to tridiagonal form into a 2 stage, one which is really compute intensive, and one which is really memory bound. Okay, so this is this is a different approach taken compared to LAPACK. And, the compute intensive part, you can clearly see that, you run, this is smooth and using your entire system appropriately. You don't have idle time. You don't have this fork and join. And, this is the curve that you get. And then you have a shift there, a switch there. And this is actually when the 2nd stage jump in. And this is when the memory bound algorithm jump in. This is actually the bulk chasing procedure that we are using there. And if you look at the memory, you have a jump in the memory as well, right? So it was really neat to see that. Okay, so the whole idea of the slide here, we're using, let's say we're using 48 core to do such reduction, right? So the first stage, again, is very compute intensive. I'm using 48 cores, in a very efficient way. All of them are busy, but the 2nd stage is memory bound. You don't need to go to 48 cores. Maybe one socket of 12 core in your Magny Cours system is enough just to handle it. But we want the runtime to be able to detect that, okay? We don't want to tell the runtime, hey, listen, this thing, this is memory bound. No, we want the runtime to detect that he has idle workers sitting there, and instead of, make them spinning and using useful CPU power, we want the runtime to tell those guys, you know what, you need to go to sleep now, okay? And there is this technology called DVFS, Dynamic Voltage Frequency Scaling, which allow you to do that. And this is still a work in progress, but this is, we think we have definitely the right application to show that this thing could work effectively. Okay, so So that was the dense, really the dense part, the dense algorithm part. And then when I moved to KAUST, I had to do other things, not really related to dense, but so this is one of the applications that I worked with Ryo Yokota. He's a computational scientist working at KAUST. And he has a simulation, this n-body simulation. And this is used as a core kernel for astrophysics and turbulence applications. So you have many particles sitting in a certain 3D space domain, and those particles interact with each other, and interact with each other. And they, at each time step, you have to calculate those different strength or forces and the different movement as a consequence to each of those particles. So, and if you look at his kernel, he has, I think he has 1, 2, 3, 4, 5, 6. He has 6 kernel. Okay, he has 6 computational kernel. So when I've seen the first time his code, I said, "Oh, great, 6 kernel. This is his task. I can throw in my QUARK stuff, and we're gonna do some dynamic scheduling, especially because his stuff is really load imbalanced." And when I thought about it, when we used QUARK for usual dense stuff, we don't have that much load imbalance in the dense world, okay? So you don't have, it's very well, balanced most of the time. You have a pattern, and, things are very clearly laid out. In real simulation, it's not really the case. You have really to deal with, load imbalance issues, and having a dynamic runtime should help a lot. So this is why I really jump in and look at his code. And when we looked at it, it happened that only those 2 kernels, M2L and P2P, are the most compute intensive. Okay, the others are, in terms of, we did the zip proof on it, and in terms of elapsed time, those are a very fast kernel. Okay, and the main guys are M2L and P2P kernel. So this is what we focused on those 2 kernels. We wanted to wrap those kernels with QUARK interface, okay, and then just feed it to the scheduler and see what happened. And when we started doing this, we started at the low level, okay, so at the level of the kernel, we put QUARK there. And at that level of the kernel is just, calculating the interaction between 2 particles. So the granularity is very small, okay? So it's compute intensive, that's true, but the granularity is still very small to hide the overhead of the scheduler that we are using there. So, and I guess I need to move to the next slide. And with these issues, we had another issues. We had to go breadth first in his application. We had to change a little bit his application to go breadth first, such that he could expose to the runtime as soon as possible, the different parallelism, the different parallel tasks. And this is what we get as a DAG. Okay, there are a lot of dependencies going on. And if you use no mutual interaction, so there is with mutual interaction and no mutual interaction, you can get a better DAG that way. And each of those nodes, this could be just a single interaction between 2 particles, but we had a parameter on top of it which could define the granularity of the task. Meaning, we could have a task which do multiple interactions together. Okay, we try to increase the granularity. So think of this DAG here, where each of those nodes can be actually a super node, meaning it's not doing only a single interaction, but doing multiple. All right, so here are the performance. Q here. Well, let me. Okay, so this is a speed-up graph, strong scaling with QUARK. So we have the number of threads here on x-axis, and we have the number with the speed-up in the y-axis. And there are 3 curves. Q corresponds actually to the number of interactions. This is your granularity parameter. Okay, and as you increase your granularity, you make your actual kernel, huge kernels or super kernel, more compute intensive. Okay. And especially you can hide the overhead of the scheduler. In dense, when we use QUARK, well, QUARK, he had to deal with gems, big gems, well, of 200 by 200, but they are big enough to be able to hide the overhead of the scheduler. Here, when we went to FMM stuff, we had to play again with this granularity, okay? And well, we get a linear speedup. When you get a linear speedup when you go to high number of particle interaction, compiled all together in one task. Okay, and this is the actual runtime. This is the tracing, not the runtime. This is the tracing on 1, 2, 4, 8, and 16 core. and this is the actual timeline. So this is when you run one core, this is the trace that you have, and 2, and 3, and 16. And you can see that you don't have, it's pretty well balanced. Okay, well, the dynamic runtime make it pretty well balanced. Okay. So what is next for this work? A heterogeneous architecture with hardware accelerator. This is the next thing we want to do. Here we're only using QUARK, so only x86. We want to use StarPU, of course, to be able to handle those super tasks, to be able to have those super tasks handled by some GPU hardware. We want to look at some, eventually, a distributed memory system using the DAG approach, okay? Because, I mean, ideally, the plan is to try to start the next time step. I mean, think of this FMM being done in a single time step, right? But you have this FMM being called at each time step, all right? So what we want to do is that try to start the next time step while, the computation on the previous time step has not been done yet, has not finished yet. All right, seismic application. So this is the last benchmark or toy. We are currently looking at it. It's still a work in progress. I'm sure all of you are familiar with this. So the idea is to get those reflected waves from those aerophone, and this can be modelized with some acoustic wave equation with constant density. There is this reverse time migration scheme that we heard in a previous talk that is a common thing to use those days. So there are two different cases here. So there is this isotropic case where your stencil depends only on axis direction X, Y, and Z, and you have this titled transverse isotropic TTI case where you have to add as well the cross derivative. Okay, so in other words, this is your stencil point. Okay, for the isotropic stencil, and with TTI you need to add the different derivative, cross derivative into your stencil scheme. So this is so I'm going to show some graphs here, some cartoons here. So think of this is my just for simplicity purposes. This is 1D one-dimensional in space here, and this is my time here. And I'm doing some sort of domain decomposition, okay? So I have my GPU 0 here and GPU 1 here. Forget about the host right now, because this is really the ideal case that we are targeting to show some how we could reduce data motion between GPUs for that particular stencil, and how to reduce synchronization as well. So this is the explicit time integration scheme with domain decomposition, and the usual way to do, well, the really standard or basic way to do it, you compute, each GPU compute the next time step, right? And then they have this hello exchange. They move to the next time step and a hello exchange. They move to the next time step and hello exchange, and they repeat it, right? So there are some work trying to overlap the communication of those hello points, where they would calculate first the hello points, and then they send it asynchronously to the GPU, and then at the same time they will finish finish calculating the other contribution within the domain. So this is another approach. But here the idea is that from when you look at the basic implementation, you have to communicate each time step, and you have to synchronize as well. Okay, you can't start the next time step if you are not done with the previous time step. So the idea is that you want to introduce some communication avoiding, okay, by reducing the hello exchanges frequency. So in terms of data volume, it's going to be exactly the same volume that you're going to communicate between two GPUs, except that you're going to win in latency. Okay, so the idea is that you do some instruction reordering. There is nothing really new there. I think the first keynote speaker of the workshop, talked about it. You want to do space and time together. I think he called it temporal blocking. So, the idea is that what you do, you have two phases. The first phase is that each GPU calculates the element in its domain. Only those elements which don't require information coming from your neighbor, okay? So what's happening is that the black points here are being calculated by the current GPU, and the white one are getting delayed. I don't compute them right now, okay? And by doing this, you have a first step which is really embarrassingly parallel within each GPU, okay? And once you reach a point, a certain certain time step here, which is a tunable parameter, okay? So what you do, you need to compute now the solution within this inverted cone kernel. Okay, so I know on GPU 0 memory I have this data, on GPU 1 memory I have this data right here, and this is the missing data that I need to compute now. And the idea is that once GPU 0 and 1 are done with their first phase, GPU 1 is going to send to GPU 0 all the data located here on the boundary, only the data located on the boundary. And then GPU 0, he has this data located on its own memory here in the boundary. He's going to use this one to just fill out this box or this inverted cone kernel. So you have really one step which is embarrassingly parallel, and at this time you're gonna now synchronize, but you don't synchronize at each time step. You rather synchronize at a certain window size, a Windows time size, and you communicate a bunch of data all together. So you definitely win in latency there. And once this is done, you have a second step which computes the data within this inverted cone. And then when you're done, well, you start over. Okay? So how actually the dynamic runtime system fit in this whole story? I didn't mention anything about it, but in some cases you do have some in some numerical scheme. So you may have this PML, right? You may have this PML that you have to compute those absorption layer, boundary layer, which they are really compute intensive compared to the points located within your domain. So you definitely, if you were to trace your application where you have PML boundary condition, you'll have really load imbalance. Those who are located, the guys which are located in your boundary of your domain, they will crunch numbers and do useful work, while those which are located in the central of the domain, well, they will just stay idle there. Okay, and the idea is that you want to use a dynamic runtime again to to balance the workload between the different threads, and even try to, again, this idea of trying to compute ahead of time as soon as possible, as long as the dependencies are satisfied. So there are no numerical instabilities, right? So you're just doing instruction reordering here. So there are no numerical instabilities introduced in the original scheme, numerical scheme, and you don't have any redundant computation, although, of course, I know that flops are cheap on the GPU, but you don't do any redundant computation here. It's very similar to some extent to this GMDML approach for this matrix power kernel. And this is work in progress with my student, PhD student, Ahmed Abdel Fattah, and Saudi Aramco, which is sponsoring him. All right, conclusion. DataFlow programming model could play, I believe, a major role for exascale challenges. So you need efficient runtime with high productivity in mind. Okay, I think this is really crucial. To make sure that the community is behind it and will be using it. But at the same time, it's not a matter of having this runtime. As I mentioned, this Morse project is all about. You need to come up with new, flexible, asynchronous algorithms. So I showed that it worked potentially for dense, and it could work as well as for sparse computation. And the whole idea again is to determine the right granularity, such that you can hide the overhead of your dynamic runtime scheduler. With that, if one of your questions is what's beyond exaflop, here's the answer. You have Zeta, Yokota, Xona, so this is not the end of the race at exaflop. Okay, so I guess I have one question less. Thank you.